Welcome, I'm Giacomo Titano. Thank you for your presence. Thank you for your presence for this mini symposium that I suggest to permanentization. The title of the mini symposium is Energy Methods for Fatigue Assessment. And we have six presentations. For each presentation we have 15 minutes. The discussion of all the presentation is at the end, I think at past 5. Okay, the first presentation is of Oleg Plegov, Alexei Wiklov, okay, Anastasia Ivanova, Alexander Zakharov, and Valery sorry. The heat dissipation at the fatigue crack and the mixed model plotting. Please plot use the 5 minutes, 15. And 2 minutes before then, I make a signal to you if you want.
Okay, thank you very much. How we can...
There is a switch?
We don't have it.
Okay.
It is not
Okay. You are poor.
Sorry.
No. It's okay.
Okay. Thank you very much, everybody, who participated in this session, and thank you very much to Giacomo for organizing such small session with a lot of people which know in one to another, and it's a good opportunity to discuss our current work devoted to energy dissipation and practical application of infrared thermography for study of crack propagation and for study of deformation, plastic deformation of solid. The title of this work is Heat Dissipation and Fatigue Corrective the Mixed Mode Loading. I'm going to present some results of ongoing work. It's not finished work, unfortunately, but I think it would be interesting to share with you the current results and discuss maybe possible continuation of this work. This work is carried out in collaboration of our institute. So next slide will be not motivation, but general idea of where our institute is located. It's a collaboration of our institute, Institute of Continuum Media Mechanics, Russian Academy of Science, with Kazan Scientific Center. We have some experience in application of infrared thermography in Kazan. We have very excellent laboratory with good experimental facilities for multi-axial loading. So this slide you can have an idea about size of Russia, and we are located just in the geographical border of Europe.
Do you listen to the music?
Next slide. Present outline of my presentation. I will speak about motivation, but I think it's not very important to speak about motivation to apply infrared thermography in this room. After, I will speak about our natural results with Dr. Baer, which give us an impulse to find some solution for approximation of heat dissipation from a crack tip. And these results give us natural continuation of this work, study to mixed mode loading and find the approximation of heat dissipation under mixed mode loading. So, motivation, let me start from temperature evolution into a crack tip. You can see very beautiful from my point of view the picture. No, only one time. Okay. So, but we can easily to see thermoelastic zone, monotonic plastic zone, cyclic plastic zone, and we have it's very beautiful. But all in all, it's only temperature. The infrared thermography gives us unique possibility to measure the temperature. But if you want to make some model or to write some thermodynamic potential, you have to derive, you have to estimate the energy balance. And if you go to plasticity, for example, 70 years ago it was published by Frondenthal, the energy concept may be one of the main concepts to describe the plastic deformation. If you consider that plastic deformation of solid, it's a very complex hierarchical system with several special levels and quite complex defect evolution on each level and interaction. It's possible to describe, and in our institute we have some work, but generally if you have a key for each level, energetic balance, you can to estimate the energy balance. So for crack tip, there is a very well technique proposed, as I remember, it's published in paper of Krazokas, when you estimate the heat exchange between your samples and environment and solve.
Sorry. Yes, but it's
okay. If you need some motion compensation, you need some filtering after you solve the back problem, and the main problem in this situation, it is the T parameters which describe the interaction with environment. If you are working in dynamic loading, it's no problem, it's quite fast process, but if you are working with body static and cycling, the tau parameters, it's quite big and quite important. And sometimes it's quite difficult to estimate. There is a well-known technique for estimation. I'm not going to detail, I guess everybody knows. We do additional experiments with local heat sources and to find the tau as fitting parameters for equation when we are sure that there is no additional sources in our samples. So we can take tau parameters and we can estimate the heat sources map in our samples. But every time, yes, here you can we are presenting estimation of T parameters, and finally it's heat sources. We've chosen tau for some samples. It was 40. But generally, for me, every time it's a problem when you try to estimate these tau parameters for each sample, and in collaboration with Dr. Bear and with Institute of E2M, we developed contact sensor, which give you opportunity to measure the heat flux from the sample, integrated heat flux, and compare with results obtained by infrared thermography. So here, this picture presents the final view of sensors made by Professor Bear in her institutes, and here you can see the idea. The idea is quite simple. We have one PTA element as a measurement element, the second one as a cooling element, and electronics, which keeps the first element every time in the same conditions. Finally, we measure the integral heat flux from the sample. It's very useful, for example, if you are working with quasi-static tests. It's just quasi-static test, extension, and you can use this sensor to measure when dissipated part of the energy. If you have stress-strain curve, you can automatically take the stored energy part and fill the energy balance in your samples under quasi-static tension. Here you can see the examples for, I don't remember what kind of materials, but we have a lot of tests for simulation and for measurements of energy balance under quasi-static tension. If we are going to crack propagation, it's not so easy. Here you can have an idea about experimental setup in our institute. We have infrared camera and contact heat sensor from another side of the samples. And we are comparing both results. The main advantage of a sensor, advantage and disadvantage in one time, we have integral heat flux, but we can do it from the beginning to the end of one experiment. Here you can see the characteristic line of which shows you the heat dissipation from the crack during fatigue crack propagation experiments. And red line, it's infrared thermography movies, which treated as it was shown before, and we are compared the integral value of heat dissipation from infrared thermography. So it's not so bad corresponding, and we can use this energy for investigation. So, and now we can go to a crack tip, but it's one of my dreams, how to find, how to derive that energy balance in the crack tip. There are a lot of attempts to derive, and here it's just shown the equation which was obtained at least in two papers, in papers of Schott, and there is a work of Professor Chudnovsky devoted to energy balance, and also very, from the first look, it's unusual equation. The idea is quite simple. You write a global energy balance, you write a local energy balance, which include energy of elastic energy of elastic energy of lattice. Fracture energy, you can it's possible to describe the damage zone and plastic zone. The gamma parameters it's reflect the surface energy or damage energy in your plastic zone. And after some algebras, you have to go to the corrective, calculate the energy balance in the moving coordinate system, but it's not so difficult. And finally, you can get such equation, very unusual. Here you can see the plastic wall minus dissipated energy. Practically, it's stored energy in your sample, and under this ratio, you can see the damage energy and G integral. The G integral is not directly correlated based on this approach to crack tip. This point is quite unusual. There are a lot of work which correlate directly crack propagation with G integral. We try to do some review of work, and we find a lot of attempts to find another correlation, but it was done by Paris. You well know the Paris correlation, but there are a lot of attempts with G integral, with plastic rock, with stored energy, with dissipated energy, and we decided just to go with the Paris to correlate crack propagation with energy. Nothing more. It's a lot of people try to do it, and in our simulation, we have found in our experiments two regions of crack of energy dissipation. In the beginning, for short cracks rates, we have practically constant dissipated of energy, and after we have increasing of energy dissipation. And second, and this part is generally accepted, or we can make a line, a proportional correlation between crack propagation and energy dissipation. But this part was unusual, and we try to explain why. For very small cracks, we have practically constant energy dissipation. Also, we have very interesting experiments. Maybe Professor Ber will explain it a little bit different, but from our point of view, there is a very unique opportunity in Munich University to make experiments with constant strength intensity factor. And on the constant strength intensity factor, we observe a decreasing of heat dissipation from the crack tip. Right? Stress intensity constant, crack propagation constant, but energy dissipation from the crack tip decreasing. So we have maybe there are some problems in experimental conditions, but if we take into account that we have two unusual things: constant dissipation for small crack propagation and sometimes decreasing of heat under also constant crack, we need some explanation for it. And we find very funny work which was published in 1965. In 1965, Dixon published experimental work and connect elastic strain into the crack tip with real plastic strain in the crack tip by quite simple equation. You can see here it's elastic solution, it's real strain, and here you can see elastic modulus and second modulus of plasticity. Quite simple. And if it's true, but it was written in this paper, but it's results of experimental results, you can easily, at least you give opportunity to analyze your strain, real strain in the crack tip based on elastic solution. From my point of view, it's unique. You can estimate energy dissipation, first of all. But second of all, you can go to the multi-axial loading. Elastic solution in multi-axial loading is quite simple. And yes, I see. And energy dissipation is, you can estimate this energy dissipation. So we decided to do it, first of all, to multi-axial loading, to measure the energy dissipation and to check is it the same peculiarities as it was in our uniaxial loading. And we try to find some analytical solution for description of energy dissipation from a crack tip. If we take into account the results of Dixon, and after there are some papers of Raj in 1972, which try to derive cyclic plastic zone and monotonic plastic zone. And I'm not going into detail in mathematics, but you can estimate easily the plastic walk both in monotonic and the cyclic zones. And the main results of this consideration, that dissipation in reversible plastic zone doesn't depend on the crack rate. The crack moves, the reversible plastic zone moves, and dissipation is practically constant if you take into account this algebra. And monotonic plastic zones depends on the crack advance. So you have two different mechanisms: reversible, which independent on the crack velocity, and monotonic, which is a function of crack velocity. And after we propose such phenomenological equation, which describe plastic walk in the crack tip and practically heat dissipation from the crack tip. It's a function of stress amplitude, first items, and second one is a function of crack propagation rate. And here you can see all experiments which was made by Professor Baer, and this equation very well fit practically all stress level which was observed, and also our experiments. So, and next step, try to go to multi-axial case, and we started experimental program with Kazan Institute of Russian Academy of Sciences. Here you can see the experimental setup. Next slide presents the heat dissipation, crack length versus time, heat dissipation from the time, and Paris curve for different coefficient of biaxiality. And also the situation is quite similar. We have constant heat dissipation and after increasing of heat, like it was in uniaxial tension. And if we do the same treatment it was before, we try to find a correlation between heat and crack rate. For second region we have direct correlation, which was expected, and also we can find a part of the first region when we have a constant heat flux, which we correlate with some amount of multiplication of heat dissipation and crack length. So I'm sorry, just 1 minute more, but I'm not going to speak about it. Just few points from my point of view. We have very interesting possibility to divide the dissipation from the reversible and monotonic plastic zone. It gives us some phenomenological equation which can be used for description of energy dissipation. Up to now, we have at least 2 experimental results which prove this idea. In multi-axial loading, we observe the same character of energy dissipation, and we can propose at least an explanation for some peculiarities of dissipation and uniaxial loading. Thank you very much for your attention. Piece of Russia, I was expecting it would be very hot in Belgrade and take some Israel picture in our region.